Whitened clip as a likelihood surrogate of images and captions. Clip is a very powerful vision language model that learns to align images and text into a shared embedding space. But despite its success in many downstream tasks, it lacks a clear probabilistic interpretation. Such a probabilistic interpretation can be useful for a lot of downstream applications. Language models explicitly approximate such an interpretation through the negative log likelihood training loss. Classic image analysis methods used to explicitly approximate such a function based on some prior knowledge. Deep learning methods that have advanced the image analysis field greatly in the past decade and a half only implicitly approximate a probabilistic function. We propose a direct, explicit likelihood approximation using CLIP. If each CLIP embedding is this small vector x1, x2, we have a large X matrix. Each of these embedding vectors is of dimension d. This is the mean embedding, and these are the centered embeddings. We can use them to calculate an empirical covariance matrix. Using this covariance matrix, we can compute a whitening matrix, W, which is not unique and can be computed in many ways. We use PCA to do it. The whitening transform, once W is obtained, is applied on the centered embedding, not on the raw embedding. What are the advantages of using this whitened embedding space? It's purely data-driven. It's an invertible transform. We compute W once, and then we can use it in inference time efficiently. And the whitened features have zero mean and unit variance. We now compare between the regular clip embedding space and the whitened clip embedding space. In the regular case, the covariance matrix is not diagonal, meaning that features inside the embeddings have correlations between them. In the whitened case, the covariance matrix is diagonal, indicating no correlation. Now, when we look at the different features on a big group of samples from MS-COCO validation set, we can see that each of the features has a different variance and different mean. When we're looking at the whitened space, all of the features have zero mean and a unit variance. So they are identically distributed, approximately Gaussian, and so non-correlation indicates independency. So if we have a group of IID standard normal distributed vectors, then this is their likelihood function, and this is the log likelihood. This is a very simple equation with a constant and the norm of the whitened embedding. So using CLIP and the whitened transform, we can get a very simple and direct log likelihood function for images and for captions. Now we will show a few use cases of this likelihood. First, we can see here real images and AI-generated images with artifacts like 6 fingers and a blue dog. We can see that the scores of the real images with no artifacts are higher and more likely than the scores of the artifacted images. In addition, we can look at these captions, starting from this caption with many names in it. Whenever we reduce a name, like instead of Minnie Mouse, a mouse, the norm goes down and the likelihood goes up. On the other direction, if we take a pretty generic caption and make it more specific, instead of a woman, a bride, or Jenny, the norm goes up and the likelihood goes down. Here we performed an experiment with ImageNet R, where we have similar images in different styles, different domains, similar domains to real images like graffiti are pretty similarly distributed, but not realistic domains like sketch or video games are very out of distribution, which means higher norms and lower likelihood scores. And we also identified generation model bias. We used the unclip framework, and when we took an image and generated another image using the exact embedding and tested the likelihood of the original embedding and the new image embedding, we can see that the new images have lower likelihoods compared to the original images. So we introduced WClip, an isotropic variation of the clip embedding space. This is the first direct likelihood approximation using the clip model. The likelihood approximation is sensitive to text complexity, artifacts and images, domain shifts, and it identifies a generation model bias.